Hello, welcome to Algebra 2 Common Core. Today we're going to investigate inverse functions. We're going to be doing an exploratory exercise first, where we consider the two functions f of x equals 3x plus 7 divided by 2, and g of x is equal to 2x minus 7 divided by 3. So for the first part, we want to evaluate f of 5. So to find f of 5, we are substituting the number 5 in for x into the function f. So we're going to say 3 times 5 plus 7 divided by 2. Calculating that, we're going to do the numerator first. So 3 times 5 is 15. 15 plus 7 is 22. 22 divided by 2 gives me an answer of 11. Let's go on to do g of 11 within this same section. So we want to say 2 times 11 minus 7 divided by 3. 2 times 11 is 22. 22 minus 7 is 15. 15 divided by 3 gives me 5. Let's do something similar for part B. In part B, we want to calculate f of 0. So substituting 0 in for x into my f function, I'm going to say 3 times 0 plus 7 divided by 2. This is giving me 7 halves. Now let's calculate g of 7 halves. And that's going to involve a little bit more mental math here. 2 times 7 halves minus 7 divided by 3. Now, of course, when we're doing 2 times 7 halves, we're going to cross cancel the 2's. So 7 minus 7 is giving me a 0 in the numerator. 0 divided by 3 is just 0. Now take a few seconds to look at those two examples and see if you notice anything. Do you see that when we started with a 5 in our f of 5 function, we got the answer of 11. But then when we put 11 into the g function, that brought us back to our original x value of 5. The same thing happened in part B when we started with 0 for our input. Our output was 7 halves. And then when we put 7 halves into the g function, it brought us back to that original input of 0. What we can see here is that these two functions are called inverse functions. They reverse each other. As I put an input into the f function and then take the output and put it into the g function, it brings me right back to my original input. So let's take a look at some composition of functions using these two functions. I see that I am starting with a function, I've got f of g of -1, so I'm going to start with -1 and of course put it into the g function first of all. So remember how we write this. -1 gets replaced in g, and when we do that, we've got 2 times -1 minus 7 divided by 3. This is giving us an answer of -3. Now we're going to take that output from our g function, -3, and we're going to replace the x in the f function with -3. 3 times -3 plus 7 divided by 2. -9 plus 7 is -2. -2 divided by 2 gives me an answer of -1. But that's exactly the same x value as I started with. That was my original input. F and g are inverse functions. So when I use both functions on that input of -1, I end up getting back to the -1. Take a look at what happens in example D when I'm starting with an input of 5. I'm again going to substitute 5 into the g function first of all. And when I do that, I've got 2 times 5 minus 7 divided by 3. 2 times 5 is 10. 10 minus 7 is 3. 3 divided by 3 gives me a 1. Now take that 1 and substitute it into the f function. So we've got 3 times 1 plus 7 divided by 2. That's giving me 10 divided by 2, which is 5. Now technically, if I see that I have inverse functions, I don't even have to do all of the substituting. If I've got inverse functions, I'm automatically going to be brought back to that 5. So we're going to take a shortcut on this next one and say, if I take pi and plug it into the g function, I'm going to get some output. It's a pretty complicated output because it has a pi in it. But then, since f and g are inverse functions, when I put that back into f, I should get back to my original input of pi. So without even doing the calculations this time, I see that I'm getting back to pi. Now we were not told ahead of time that f and g were inverse functions, but by looking at all of these examples, we can see that the two functions f and g reverse each other, and that's why we're going to call them inverse functions. So what are inverses? Taking a look at this diagram, we can see that if we start with an input a, and it happens to be in the domain of f, when I substitute a into the function f, I'm getting an output of b. Now, since I've got two functions that are inverses of each other, when I then take b and I substitute it into the function g, it's bringing me back to that original input of a. So we can say as a definition, inverses are functions that undo or reverse each other. In exercise number 2, if I'm starting with the point -3, 5, and I see that it's on the function f of x, then what about the inverse? Well, we know that the inverse reverses it. What does it mean to reverse? Reverse is actually going to mean, in this case, we're going to take xy and we're going to find the inverse. And when we find the inverse, it becomes y comma x. So the choice that we're going to pick is choice number 3 because we have reversed the x and the y coordinates. Our inverse function notation looks like the following. F with a superscript, or it looks almost like an exponent of -1 of x. That notation stands for the inverse of the function f. Now, how are we going to know if a function does have an inverse? It actually has to do with something that we've been talking about in the last few lessons. A function is going to have an inverse if it is a one-to-one function. So, any function that is a one-to-one function has an inverse. Now recall from our last lesson that in order to know if a function is a one-to-one function, we can use the horizontal line test to tell if it has an inverse. That will tell us if it's a one-to-one function, and if it's a one-to-one function, then it's going to have an inverse. Now in our next few examples, we're going to take a look at finding the inverse of a function. We're going to see that there are 3 different ways of looking for an inverse of a function. You'll recall that if we want to find an inverse of any ordered pair xy, when we do the inverse of that ordered pair, it's going to give us the new ordered pair y comma x. So, in our first example, we'll see that we are starting from a set of ordered pairs. Now, our set of ordered pairs can either be a list of ordered pairs in a set, or it can be a list of ordered pairs given to us in a table of values. So regardless of which way we are given a set of ordered pairs, we can find the inverse by reversing the x and the y. So we would write this example this way. F inverse of x is the new set, and we're just going to reverse the x and the y coordinates. -3, 2, 1, 4, 5, -3, and 6, 1. That would be our inverse set. If we're given our original function as a table of values, then we can write the inverse as a new table of values. I'm going to write it this way, where I have x and f inverse of x. Remember that we're just going to reverse the x and the y coordinates. So we're going to say 0, 4, 2, -3, -5, 1, 6, 9, and 3, 0. This is a table of values for our inverse function. Now hopefully you're starting to recall that back when you were in geometry, you learned that reversing the x and the y coordinates is actually one of our transformations on a graph. And that transformation is shown in this graph right here. If I'm starting with the function f of x, it's a reflection over the line y equals x. So this is the transformation that we are actually doing. We are reflecting our original graph over the line y equals x. So this dotted line that we have shown is actually just the line y equals x. So you'll see that if my original function was given right here, when I reflect it over the dotted line, it's giving me this new function, which is of course called the inverse function. So we can use that property of reflections over the line y equals x to do the next two examples. So for example A, we're given the function f of x is equal to 2/3 x minus 2. The easiest way to find the inverse of this function is to create a table of values showing the ordered pairs of some of the points that I see on this graph. So you'll see that some of these points are highlighted. I'm going to write down those ordered pairs. -6, -6, -3, -4, 0, -2, 3, 0, and 6, 2. You can check those points on your graph as well. Now I want to find the graph of the inverse, which means that I am going to reverse the x and the y coordinate. So I'm going to say my new x is what my y used to be. The first point doesn't change, -6, -6. The second point becomes -4, -3, -2, 0, 0, 3, and 2, 6. So I'm going to plot those points on my graph. -6, -6, -4, -3, -2, 0, 0, 3, and 2, 6. Connecting those points, that's going to be the graph of my inverse function. So I'm going to label that f inverse of x. You'll notice that if I fold my graph along that diagonal dotted line, it would actually be a reflection over the line y equals x. So the red dotted line is that line y equals x. Let's do the same thing for example B. So I'm going to write down what my ordered pairs are. So I have 0, 1, 1, 2, 2, 5, and 3, 10. Now to find the inverse function, let's reverse the x and the y coordinates. So I've now got 1, 0, 2, 1, 5, 2, and 10, 3. Now take a minute to plot those points. 1, 0, 2, 1, 5, 2, 10, 3. So the graph that I am drawing now is the inverse graph of the one that we were given. Again, you could draw in the dotted line representing y equals x and see that this new blue graph is the reflection of my original graph. My original graph was my function f of x over that dotted line, that diagonal line, y equals x. Our last set of examples deals with finding an inverse function algebraically. There are two steps to finding an algebraic inverse function. We've been doing the first step for all of our previous examples. We are just going to, first of all, in our equation, switch the x and the y. But then, because we want to be able to graph or we want to write our function in function notation, we are then going to solve our equation for the variable y. So these two steps are necessary to find the inverse algebraically. Let's try the first one. Y equals 2x minus 1. I'm going to switch the x and the y, so this becomes x equals 2y minus 1. But then I'm going to solve my equation for y. So I'm going to add 1 to both sides of the equation. So I now have x plus 1 equals 2y. And then I'm going to solve for y. So I'm going to divide both sides by 2. So y is equal to x plus 1 over 2. This equation would be the inverse function of the original equation. I could check that also by doing the graph of this function as well as the original and see if they would be the reflection over the line y equals x. Let's try the next one, in which case we're given our function as an f of x. If that happens, what you might want to do is start your equation with a y equals instead of an f of x. Remember that y and f of x really mean the same thing. But now I'm going to need to go through my steps. So the first step is to reverse the x and the y. So x is equal to 1/4 y minus 2. Then I want to solve for y, so I have to add 2 to both sides of the equation. So I now have x plus 2 is equal to 1/4 y. But to get the y by itself, I'm going to multiply both sides by 4. So I'll have 4 times x plus 2, or I could distribute that as 4x plus 8. Now, because my original function started as an f of x, I would normally write the inverse then as f inverse of x is equal to 4x plus 8. Let's finish with the last example, which is not linear this time. Again, we're going to switch the x and the y, so x is equal to y cubed plus 1. Then we're going to solve for y by subtracting 1 from both sides of the equation. Now remember, we want to undo the function with the y, so we want to undo the cube. To undo a cube, we take a cube root. So this inverse function would be the cube root of x minus 1. Now, all of these are based on the fact that our original function was a one-to-one function. We could always go back and check to make sure that they were originally one-to-one functions by doing the horizontal line test. If you have any questions about this, please come to see me in the morning, and we'll be practicing some more in class with inverse functions. Have a great night.